All right, so we're going to finish up section 11.2 by looking at the last type of series, which is an infinite series. So compared to what you guys did yesterday, the finite series, finite means you're adding up a certain amount of numbers and you're stopping. It is always possible to find the sum of a finite series, always. Because even if it had billions and billions of numbers to add up, you can do that. You can add up billions of numbers. But infinite, that's kind of a different idea to think about, right? If you add up infinitely many numbers, what do you think happens when you try to add up infinitely many numbers? Anyone have an idea of one thing that could happen? Yeah?
You can't add them all up because there's always going to be more.
Okay, so we can't add up infinitely many numbers by any kind of direct calculation. So we've got to come up with kind of a different way to think about it than actually doing it all out by hand, because it's impossible. Do you think when you add up infinitely many numbers you would get an answer? Or do you think it would approach infinity? Or negative infinity? Yep. It can sometimes. So if you're adding up numbers in a sequence like this, hopefully you can see the pattern there. That would definitely add up to infinity. If you kept going forever, it would add up to infinity. There would be no limit to what those add up to. It doesn't approach a value. Yep?
Couldn't it also approach 0? If it goes between positive and negative?
0 is a possibility. It could approach 0. In this case, if these were alternating positive or negative, it wouldn't approach. It wouldn't really approach anything, right? If it was like 2, -4, +8, -16, +32, it's like it would just keep bouncing back and forth between bigger and bigger positive and negatives. But think about if you did something like this. What's happening to my number each time? Yeah, specifically by how much? Yeah, it's getting half as big. When you are adding up infinitely many terms, and the terms are getting smaller and smaller and smaller that you're adding each time, eventually you can kind of think of it as they're going to get so small they don't even make a difference anymore. So yes, there's infinitely many of them, but they're also getting infinitely small. So we could actually find an answer for what everything here adds up to. Right? And we're going to take a look at how to do that. I think if you added up every number in this sequence, starting at 12 and continuing the pattern that I did forever, I think it would add up to 24. I think it would add up to 24. Yep, it would add up to 24. Okay, so this is an example of a series that when you add up infinitely many terms in it, you actually get an answer. Right? Now, one thing we're going to make clear is there's a difference between what all of these terms added together are approaching and what the individual terms in the sequence are approaching. Okay? We don't know how yet, but adding all these terms together approaches 24. Okay? I'm going to show you how you get that. But adding all of those together, it'll never hit 24, but it'll get extremely close, like 23.9 repeated. It'll get very, very close to 24. But the individual terms, what are the terms going to get closer and closer to if we continue the pattern? Yep.
0.
Right. The terms themselves are approaching 0. The sum of the terms is approaching 24. So there's an important difference. You got to read it carefully when you're answering the question. Okay, what do they want? Which one of those do they want to know? You might also see it worded a little bit differently. Instead of the sum of the terms, you might also hear it called the limit. So if I asked you, what is the limit when you add together all these terms, it means I'm asking for what is it getting close to. And that would be 24. So the notation for an infinite summation, very similar to yesterday. The only difference is the stopping value is not fixed. It goes on forever. So that's why we have an infinity at the top. And when you expand it and write it in expanded notation, it ends in an ellipsis, which means it keeps going. So if you had to expand an infinite summation, you'd probably just do the first 3 or 4 terms, and then we'd put an ellipsis to say that it goes on forever. Once you've established a pattern in the first 3 or 4 terms, that's generally good enough for an expansion. So we kind of already talked about this idea. You cannot add up infinitely many terms by hand. So we got to kind of think of how to do this as a limit. Okay, think of what the terms are getting close to if you add them together. And there's a couple ways we can do that. We can think about it numerically, so we can do it on paper, algebraically, or we can also look at a picture, and we can look at a graph and see if the graph is getting closer and closer to something. Now, what do we call it when a graph gets closer to something but never reaches it? Yep, an asymptote. So that's exactly what we're going to look for when we add up infinitely many terms graphically. We're going to look for an asymptote. Okay, are we getting close to something? If we are, then whatever we're getting close to, that's what they would add up to. We have to figure out the number we're getting very close to. And that's what this idea is kind of expressing right here. So if there is, that's the letter S, that's not a 5. So if there is some number S, we're using the letter S to stand for sum, such that if you graph the line y equals S as a horizontal line, and then your partial sums look like they're getting close to that asymptote. So it might look something like this. Here's an asymptote. And when you add up the first term, you get this. When you add up the first 2, you get that. First 3, first 4, first 5, first 6. What we can see is that as we add up the first n terms, it looks like they're getting closer and closer and closer to that horizontal line. So what we would say is that our sequence of partial sums is converging to the number S. That means it's getting close to it. Now, will it be close to it right away? No. You have to usually go out at least 6 or 7 terms. And usually that's enough to tell. If you go out the first 6 or 7 terms, you're going to see you're going to get close to something. Now, if your partial sums did something like this, let's say the first one was here, then you had one here, and then here, here, and then there. That type of graph is not going to converge. What the blue dots are showing is as you continue to add more terms, the answer just is approaching infinity. So that's maybe where you're adding up numbers that double each time, right? Like 2 plus 4 plus 8 plus 16. What you're adding isn't getting smaller. It's doubling. So it's not going to converge. In that case, we say it diverges. Okay, so converging means that you're adding up infinitely many things and it's getting close to a value. Diverging means you're adding up infinitely many things and it's not getting close to a value. Okay, but that's the whole key. Can you figure out that number S? Okay, that is your horizontal asymptote. Okay, so we'll do a little bit with the graphing calculator. I don't think you're going to need it though, but you can just watch me do it. And then we'll talk about how to do it without graphing. Okay. Also, remember, when you use the graphing calculator, it's not going to do the purple dots like that. It's going to do them like this. But when we're adding terms in a sequence, remember, there's nothing in between the sum of the first 1 terms and the sum of the first 2. You can't say, well, let's add up the first 1.5 terms or the first 1 1/3 terms. So even though the calculator is going to connect it, you have to think of it as discrete dots. Any question why it shouldn't be continuous? I think we kind of talked about that idea on Monday with a sequence. There's a first term, and there's a second term, and there's nothing in between. All right, so what we're really doing is we're looking at a sequence of partial sums, but we're just going to look at it really far away. Right? We're going to look at what happens when we add up the first 10 or the first 20 or the first 30 and just see if it's getting close to something. And visually, that's very easy to do. If we can type the formula for the partial sums into y1, then we can use either the screen or the table and look as far down as we want, and we don't have to keep going through the calculation. So remember in the homework, we had that formula. It looks something like this, A1. I think that was it. That's going to take a long time to do if we want to do it for, like, say, the first 20 terms. Right? You'd have to plug in n is 1, plug in your r, and then do it all out. And then do it when n is 2, and n is 3. If we use the table on the calculator, it can figure it all out automatically. Okay, so it's going to be a lot faster. All right, so let's look at an example. Okay, and I'm going to type in the formula, but I've already done out some of the partial sums. And I want to think about what kind of series, what kind of series can converge? What's an arithmetic sequence? How do you get from one number to the next in that kind of sequence? Yeah.
Adding.
Yeah, adding or subtracting. So think of like, let's say you start with 5 and you add 3 each time. Next number is going to be 8. And we get to 11. We get to 14, right? And we can keep going. Now, as I keep adding 3 each time, are the terms in this sequence getting closer to 0? You think, Emma? No, they're getting bigger and bigger. So adding the same number over and over will never result in terms that are going to get close to 0. They're just going to get bigger and bigger. Well, what if you subtract the same number over and over? Because you can also get an arithmetic sequence that way. If you subtract the same number over and over, will your terms approach 0? Okay? No. No. So arithmetic sequences never converge when you find the sum to infinity. It's impossible. The only kind of sequence that can possibly converge is a geometric sequence, when you're adding up infinitely many terms. Okay, so that's kind of important to remember. The arithmetic sequences, when you add up all the terms to infinity, never converge. They can't. Because the terms are either going to approach infinity or negative infinity. You have to find the kind of sequence where a term can approach 0. That only happens in a geometric sequence. Okay. So what I've done on the right side is I just expanded out the notation for an infinite geometric sequence. So you'd start with your first term, And then every time to get to the next term, you multiply that term by r. So if I started with a1, a1r is the next term. And then to get from this to the next one, I'd multiply by r again. So the next term would be a1r squared. And the next term, a1r cubed. This exponent is always 1 less than the position. Okay? This is the first position. That's the second position. That exponent on the r is a 1. That's a 2. This would be the number in the third position. And the exponent is 1 less. So that's the pattern in a geometric summation. So now, let's see if we can figure out what's going to happen in this geometric sequence. Based on the formula there, what's my first term in this sequence? Yep, 2. Okay. First term is right there. Or, if you're not sure what the first term is, if you forget that it's written right there, plug in a 1 for k and do it out, and that gives you the first term. So 1 minus 1 is 0, 1/3 to the 0 is 1, and 1 times 2 is 2. So the first term is a 2. Okay. Second term, fill in a 2. What's 2 minus 1, and then take 1/3 to that power? What do you get? Yep. 1/3, and then times 2? 2/3. That is the second number in sequence k. I'm not adding them together yet. I'm just finding the terms that this formula generates. What if you plug in 3 for k? What would be the next term? Yep. 2 ninths. Yep. And what if you plugged in 4 for k? What would be the next term? Yep. 2 over 27. So it's just following the pattern that you're multiplying by 1/3 each time. All right, so now what I want to do is find S sub 4. So you did that yesterday. That means take the first 4 terms in this sequence and add them all together. Well, I have the first 4 terms written. Okay. To add 4 terms together, it's not that hard. I can do it. I don't want to keep doing it this way because it's going to start to take longer and longer every time we add another term. But it's 2 plus 2/3. Oh, it's not pressing. Plus 2 ninths. Plus 2/27. So when you add the first 4 terms together in this summation, you get 2.963. 2.963. And I wrote it out right there. Now, a faster way of adding those 4 together, rather than figuring out what they are and then typing them all in, we can use the formula that we talked about in the homework. First term times 1 minus r to the n over 1 minus r. If you type all of that in, you'll get 2.96. So what I want to do now is I want to put that in the calculator. This is going to be my variable, and that's what changes each time I want to do the next term. Nothing else changes. You just change the power. Okay? But it's going to be a lot faster if I can use the table than to try to do this every time. All right, so we can put that in. Just have to be careful when you type it. So you've got 2 times in parentheses, 1 minus, put your r in parentheses, and that's going to be your variable, raised to the x. X is how many terms you're going to add together. That's the numerator. And then I want to divide that by 1 minus a third, which is 2/3. Okay, I'll know if I typed it in the right way if I go to my table, and when I put in 4, I get 2.96. Let's go to our table, put in 4. Perfect. So now when I put in 4, it's automatically doing this calculation for me without having to find all of those terms. When we do 5, so this would be now if you found the next term after 2/27ths and then added it to everything you already have, you would get 2.9877. And that's what the formula gives us. Okay. And then if you found the next one after that and added it in, the first 6 terms add up to 2.9959. I think it's getting pretty clear what this adds up to. What does it look like it's getting very close to as you continue writing the terms in this sequence and adding them all together? Yep.
3.
It's getting very close to 3. Yep. Eventually, it probably will say 3 because it's going to run out of decimals. Okay, if you add up the first 10 terms, now you're already 2.99999. Very, very close to 3. But does everyone see the advantage of doing it this way instead of having to find all these terms and add them up? Okay. If they actually said, what are the first 10 terms you would add together? Well, now I need to find them all. But it's not asking us to find the terms you're adding up. It's just saying, what do you get when you add them up? So we can do that without actually finding what we're adding using this formula. So now, what's happening to this? Just the part I circled in green. As n continues to get bigger and bigger and bigger. Yeah? This part right here gets very, very small. Think about 1/3 to the 6th power. A third of 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 a third. It's getting very small. And if this number goes to infinity, you're taking a third of a third infinitely many times. This part basically starts to just disappear. It becomes almost 0. And look at what you're left with. 1 divided by 2/3 times 2. Well, what's 1 divided by 2/3 times 2? What does that come out to? Yep, that comes out to 3. Okay. So when we start adding up infinitely many terms, we can actually make this formula a little simpler. We can forget about this because it's not going to make any difference at all as n gets huge. And all we have to look at is that part of the formula. It's a simpler way to think about it. Okay. And we'll write that down in a minute. Okay. I'll visualize it real quick just to show you. Set our window. X shouldn't go negative because you can't add up terms in negative positions. Let's add up the first 7 terms. We already know that it's approaching 3, so that gives me an idea for my y max. Let's go to 4. This is a kind of a visualization of what everything's adding up to, but it shouldn't be connected. So think about it kind of like, here's what you get if you add up the first term, right about there. And the first term was what, 2? Yeah, first term was a 2. If you add up the first 2 terms, that's 2 plus 2/3. That's 2 and 2/3. So go back to our picture. First 2 terms, right about there. And if you go over there, that's at 2 and 2/3. When you added up the first 3 terms, now we're starting to get pretty close to 3. That's 2 plus 2/3 plus 2/9. That would be right there. So a little bit higher. And then the first 4 terms, I think it was like 2.96. It was extremely close to 3. So that's a visualization of what the first 4 terms look like when you add them up. Ignore the parts that are connected. Just look at the 4 black dots. That's what you have to focus on. Okay, again, just focus on integer values. So we already did that. Now, as you look at those dots and they go further and further down, whatever those dots are getting close to, that's what your sum is approaching. So that formula right there, that's what you learned yesterday. This part, you don't have to cross it out in your notes, but this part is going to start to disappear as you go to infinity. It's going to get really, really small. And all that's left is that. So the formula for adding up infinitely many terms is simpler than adding up a finite amount of terms. There's less stuff in the formula. We already did that. That's the same problem I just showed you. It says to use a graphical approach. Well, that's what I did right here. That's the graphical approach. There's your horizontal asymptote at 3. So that shows you what the numbers are adding up to. They're adding up to 3. Now, will they ever reach 3? If we add them all up? What do you think? Dan, what do you think?
No.
No, they'll never reach 3. The calculator will say it reaches 3. If you plug in a big enough number for x, and even if you highlight it, it says it's 3. But if I do something a little bit smaller, like 20, you can see it never reaches 3, but it runs out of space for decimals, and eventually it just says 3, because it doesn't have enough accuracy. But it never reaches 3. Okay, let's look at this one. Let's find the sum from k equals 1 to infinity. So we're going to add up infinitely many terms. And this is the formula that's going to generate the terms. Okay. What's the first term in our sequence? Yeah? 4. Yeah. Now we're going to add the second term. What would be the second term in the sequence? Yeah? 12. What would be the third term in the sequence? Yeah? 36. I'm going to keep going, all the way to infinity. What's going to happen this time if we add up infinitely many terms? Yeah? The sum is going to go to infinity because the terms that I'm generating, they're not getting close to 0. They're getting bigger and bigger. So this particular problem, I can't find the sum. Okay, this is what we call it. This is a divergent summation. It does not converge to a number. If you graph these, it's going to look something like this. As you add more and more terms, the number just gets really big. So as you head further to the right, there is no horizontal asymptote that those dots are getting close to, and we say that that series diverges. So if the question was worded, find the limit of this summation, find the limit, you would say there is no limit. It's divergent. It goes to infinity. So we've just seen 2 different examples. We saw one example where we were able to add up infinitely many numbers, and it came out, I think it was 3. And then we just saw an example where we couldn't. Well, how come? What's the difference between the 2 examples? how could we look at this one and know that it's going to converge, and look at that one and know that it's going to diverge? Yeah?
The first one is being like multiplied by a fraction, the other one's like not a fraction.
So anytime you multiply by a fraction, it would converge?
Like the thing in the parentheses, the R.
The R?
Yeah.
So anytime R is a fraction, it would converge?
Yes.
What if I made this a
A fraction of less than 1.
4/3? Okay, yeah. A fraction less than 1 will cause it to converge. Okay? And that's what I was going to look at. We don't have to go through each one of them. But if you try graphing them and you put in different values for R, any R value less than 1 will converge. The reason it converges is because your number that you're adding each time is getting smaller and smaller. Which one of these would converge faster? A or B? In other words, like if you were pretend like the graph was a road you were driving on. I want to know which road gets to the asymptote faster. Yeah? Not B. Yeah? A. Okay? Because A is making the number smaller quicker. Right? So I can show you. Let me put in, so we had R as a third. Let's do it as 0.8 and 1 minus R to the n over 1 minus R. 1 minus 0.8 is 0.2. Wish I could copy and paste all that. And now let's type in the same problem, but let me type in 0.9. 1 minus 0.9 to the x over 1 minus 0.9. Okay, so now let's hit graph. Oh, I didn't adjust my window. Let's see. Let's set the y-max at, let's try 10. All right, so there's the 0.8, and here's the 0.9. Okay, so the 0.8, it starts, I'm trying to show you that the 0.8 levels off sooner, right? It starts to level off quicker. The red one, I mean, it's not a straight line. It kind of looks like the red one is still going for a while. It's going to level off too eventually. But the 0.8 levels off quicker. And the smaller you make that number, the faster it's going to level off. So like if you make it like a 0.2 over 1 minus R, 1 minus 0.2 would be 0.8. This is going to level off even faster. It's going to look like a horizontal line pretty fast. Okay. What's going to happen with C and D? Yeah?
They're going to diverge.
These are going to diverge. Which one would diverge faster? Yep. D. D is going to get bigger quicker. So you're going to notice it starting to curve up fast. Right? So D gets bigger quicker. But they both diverge. Anytime you have an R value that's between -1 and 1, that will converge. If you want to kind of think of it as a number line, anywhere in this green zone, that's the zone where you will converge. Because if you pick any number and multiply it by something between -1 and 1 over and over and over, it is eventually going to get close to 0. Now, if you pick any number out here, that'll diverge. And that'll diverge. Because if you multiply by a number, by anything in that red area, it's going to get bigger and bigger and bigger and bigger. Either bigger and bigger positive or bigger and bigger negative. So it's not going to add up. It's not going to converge. So we've already kind of examined what happens here. This part starts to disappear, right? When you're converging, because R would be a fraction, and if you between -1 and 1, and if you take any number between -1 and 1 and start to raise it to a power over and over and over, it gets extremely small. So this part approaches 0. All that's left is this. The part that I just circled, that's the calculation to figure out what an infinite geometric series converges to. I think I write that down. Oh, let me write it down right here. So it converges to, we're going to just neaten this up a little bit. We can multiply these two together. So we have A1 in the top over 1 minus R. So that's the formula for the sum of an infinite geometric series. Don't have to graph it, don't have to use a table, don't have to use a calculator most of the time. All we have to do is know the first term, what we're multiplying by each time, and plug it in. Now, if you apply this formula to something that doesn't converge, like let's say you tried to use this formula on a problem like this. You get an answer, but it doesn't mean anything. This formula only applies when R is between -1 and 1. You shouldn't be using this formula in any other situation besides this, because it's divergent. You shouldn't be trying to find what it adds up to. Okay. So let's look at example 4. I think it's our last one. Is this going to converge or diverge? Yeah.
Converge,
Yeah, that's going to converge. How do you know?
because R is less than 1.
Right. R is less than 1 and bigger than -1. So every time you add another term to this sequence, it's going to be half of what it was before. So it's going to approach 0. What's my first term? Yep.
5.
First term's 5. Now remember, we're not going to find the first term, the second term, the third term, the fourth term. We're not going to find them all and add them up. We're just going to use this formula to do it for us. Okay? So first term is 5. And what is the value we're multiplying by each time? That's generating the terms we're going to be adding up. Yep. 1/2. So fill those into the formula, and that'll tell you if you were to generate every single term in this summation and add them all up. This formula will tell you what they add up to. So first term is 5 divided by 1 minus R. What does that come out to? You do have to know, you can't leave it like that.
Would it be 10?
Yeah, 10. Okay, if you want to kind of if you have time and you want to quickly kind of check yourself, well, the first term is 5. The next term is half of 5, so 2.5. The next term is half of 2.5, and if you keep adding those all together, you would get something very close to 10. So the sum of the terms is approaching 10. What are the individual terms in this sequence approaching? Yep. 0. You have to understand the difference between those two questions. What are the terms approaching? What are the sum of the terms approaching? Is there any question on what the difference is? When I say approaching, again on the test, you might also see limit. So if it said find the limit of this summation, I'm just asking you, what does it add up to? What does it get close to? So that's part 2. That's infinite summations. Okay, so homework continues from the same page last night. I think we left off with 17 maybe last night. So this one picks up at question 21. So we will look at that homework tomorrow. I'll be after school tomorrow. And then we'll have our last regular test on new material on Friday. And then I'll also open the study guide, so you'll have that to work on before the final.